Hi guys, here we are with a new video of numPYNQ. Today we'll talk about our implementation. We decided to implement three functions: the sum between two integer numbers, the matrix dot product, and the correlation. Let's start with the sum. We decided to start with a very trivial function. Our aim was to focus on the overlay creation process, so that we could reuse this skill with the following accelerations. Moreover, the sum design let us demonstrate the possibility to use the Axi4 Light Control Interface and MMIO to implement overlays. These two techniques are very light, but are not the best choices if we need to transfer a lot of data. Next, the matrix dot product. This operation is one of the most used in several fields that involves data analysis. For instance, many machine learning algorithms are strongly based on this kind of computation. Our APIs make a runtime analysis to choose the best implementation for the dot product based on the matrices dimensions. So, we use a custom design if matrices are smaller or equal than 84/84. NumPy is preferred for matrices of medium dimensions. A general matrices dimensions design is used with bigger matrices when we start to have a speedup in terms of execution time. There are many software optimizations that give great performance for what concerns the floating point matrices. So, in the context of this last design, we focused on the acceleration of the dot product between integer values. Our dot product designs use both the Axi4 string control interface. In particular, the 84/84 design has a single DMA module that transfers the entire matrices to the FPGA's memory, and the implementation exploits several hardware parallelization techniques. While the general dimensions design needs two modules that transfer new data to the FPGA every clock cycle, thanks to a pipeline implementation of the product between the rows and the columns of the matrices. Lastly, we accelerated the correlation function. This operation is commonly used in the signal processing field to find similarities or repeating patterns in a signal. Our design makes use of the Axi4 string control interface and two DMA modules. Its major gain in performance is due to the possibility to load signals blocks in the FPGA's memory to implement efficient hardware parallelization techniques. To further increase the performance of our accelerated versions, we decided to re-engineer the DMA Python class. As a matter of fact, the class provided with PYNQ introduces an override due both to the calls made to C functions through CFFI and to a series of useless safety controls due to the general user-based target of this class. Moreover, no flexible management of the local buffers was provided. So, we went through all the available methods that could have been used to increase the performance of Python, and we decided to exploit the Python C API. This is a non-trivial technique that for this reason is not so common, but let the users experience a significant increase of the performance. Now, we would like to give you an overview of the results we obtained. For what concerns the general dimensions dot product design, we've been able to observe a linear growth of the speedup with respect to the matrices dimensions, and a peak speedup of 3.9x. While, for what concerns the correlation, we can observe a speedup threshold of 10.5x. This speedup threshold is reached due to the fact that the local buffers on the FPGAs are limited. To conclude, we gained more than the 50% in terms of execution time with our optimized DMA. That's all for today. Thanks for joining us, and have a look to our social media channels.